Now let's look at the shapes of the orbitals. Note, if you're following in your book, the next thing in your book was some math describing atomic spectroscopy. We're going to come back to that after we look at the shapes of these orbitals. So, Mr. Fisher Price guy, let's take a look at these. First thing to note, our wave function psi has no physical meaning. It's a mathematical expression. It has no physical meaning relating to the atom or the electrons whatsoever. It's just the math describing the electron. However, if you square the wave function, you get psi squared, you get a term called electron density. That is the probability of finding the electron in a certain volume of space around the nucleus. Note, it doesn't tell us where exactly the electron is. We cannot know that. Remember our good old buddy Heisenberg. Uncertainty principle. We don't know where the electron is. All we can know about the electron is the probability of finding it, the electron density. And so now we want to graph this electron density. We want to graph the probability, but how do you graph probability? Well, here's how we're going to do it. So, let's first look at this s orbital right here. L equals 0, m sub L is 0. And I've drawn an XYZ coordinate axis. And the way we're going to graph probability is just by putting a bunch of dots. Remember our probability of finding electron, also known as electron density? The more dots we have in a certain area, a certain volume, since this is three-dimensional, the more dots we have in a certain volume of space, the more dense the dots are, the greater density in that area of dots. So more dots equals greater electron density equals greater probability of finding the electron at that point. And so when we graph this, realize we took the Schrodinger equation, we found a wave function at work. We found the lowest energy wave function, the 1s orbital wave function. We took that mathematical equation, squared it, psi squared, and then graphed this probability, and we end up with something like this, all these dots all over the place. And if the axis, the vertex of all three axes here represents the nucleus of the atom, let's say the nucleus of the atom is right here, then this is where we will find the electron around the nucleus. And what we find is you've got a high probability, lots of electron density around the nucleus, close to the nucleus. The further we get away from the nucleus, the less chance we have of finding the electron. Now, the truth of the matter is, when we look at this function, when we look at the psi squared function, it's asymptotic, which means it never actually reaches a 0 point of probability. And so we need to look at this, okay, well, what's the shape, what's the size of this orbital? And if we wanted to encircle the entire orbital, in one way of looking at it is every orbital is the size of the universe, because the probability of finding electron does not equal 0 till you get to the end of the universe. However, it approaches very, very close to 0 very, very, very quickly. It turns out it's so close to 0 that we really can't say anything other than, yeah, I would call that 0, when it's less than a few nanometers, less than a nanometer away from the nucleus. But what we're going to do is we're going to say, okay, where is the electron? Where's the highest probability of finding it? What we're going to do is we're going to encircle or put a sphere around 90% of the electron density. Let's encircle 90% of the electron density. If I do that, I'll have a circle about like this. Now that's a circle. Truthfully, this is three-dimensional, so it's a sphere. So what we can say is, In this sphere is 90% of those dots. In this sphere is 90% of the electron density. Another way of saying it, where is the electron? We do not know for sure. But there's a 90% chance it's somewhere inside that sphere. A 10% chance it's anywhere else outside. I think that's pretty good odds, 90% chance of finding the electron there. So that's what we're going to go with, these 90% probability surfaces. Where do we have a 90% chance of finding the electron within this volume? Recall that the s orbital, that the principal quantum number n represents size. So if you had the 1s orbital that we did here and drew its electron density, if it was this big, if this was a 90% probability surface, the 2s orbital is larger. To encompass 90% electron density, you have to go further away from the nucleus. 3s orbital, even larger still. The s orbital has no nodes. A node is where the electron density goes to 0. There is no 0 electron density in an s orbital. So this is our L equals 1, our L equals 0 s orbitals. Note, it doesn't matter if it's the 1s, 2s, or 3s. S orbital is the shape. The L value gives us shape. S orbitals are spherical. For L equals 1, now we're looking at p orbitals. And when you look at the electron density for p orbitals and you graph psi squared, you get things that look like this. And so if I go in here and I circle the 90% of those dots, I create a 90% probability surface. What we see is a 90% probability surface looks like this. It's kind of like two kind of spheres, one on top and one on the bottom here. Note that these spheres, this one here, the electron density is here, but the electron density goes to 0 at the vertex here. Right here, there is 0 electron density, 0 probability of finding an electron in this xy plane. So that is a node. If you go from z, positive z, you've got a chance of finding an electron, to 0, a node, 0 chance of finding the electron. Keep on going, we've got more chance of finding the electron. So this has one node. But recall, if L equals 1, m sub L could have -1, 0, and +1. Remember, this was the orientation of the orbital. This orbital is oriented along the z-axis, so we call that the pz orbital. Another one of the p orbitals, when we circle the 90% probability, looks like this. Note, it is along the y-axis. It is oriented along the y-axis with the node, the place where there's 0 electron density, being in the xz plane. So this is our py orbital. And note, if you have pz, py, you're also going to have a px orbital. The lobes of the orbital going along the x-axis. Well, let's boost it up to, and for L equals 2, now we're looking at d orbitals with L equals 2. These are a little bit more complicated. If L equals 2, recall m sub L can be -2, -1, 0, 1, and 2. We have 5 different d orbital orientations. Note, d orbitals kind of look like puffy 4-leaf clovers. They've got 4 lobes. Note, with 4 lobes, that gives us 2 nodes. There's a node running through here and a node through here. There are 2 nodes with our d orbitals. The more nodes you have, the higher the energy. Note, each lobe here, this lobe here is between the z and the y axis. This lobe here is between y and negative z. So we call this dyz because the lobes are in between y and z. This one's tough to draw. This is dxz because our lobes are between the x and the z axis. This one is dxy because our lobes are in between x and y. This next one, the lobes are line up right along the x-axis and along the y-axis. We represent that by dx squared minus y squared. We can't call it dxy. That's this guy over here with a lobe in between x and y. Dx squared minus y squared has the lobes along x and along y. And our last orbital is dz squared, and it looks different. It's kind of funky. It kind of looks like a p orbital, a normal p orbital along z, with this kind of donut-shaped electron density volume going around it. So you have kind of this donut of electron density around this orbital, this part of the orbital along the z-axis, and that's our dz squared orbital. Note, when you add up all of these orbitals together, if you realize that all these orbitals are in the same atom, so you take the 1s, the 2s, the 3s, the p's, and put them all together, the whole electron density makes a sphere. When you look at all the electron density in atoms, you end up with spherical atoms.